Hello everybody. I hope everyone is fine. And today this will be the last GATE 2024 question I'm going to discuss. And after that I will be going through all the previous year's questions like GATE 2023, GATE 2022 and all. Okay. So this question is related with the biasing in the Mosfet, and regarding that we will also discuss some questions which is related to current mirror. Okay. So it is given that there is an NMOS transistor which is operating in the linear region and it has a current of 5 microampere. Okay, but here it is said that the VDS, the drain to source voltage of this MOSFET is 0.1 voltage. So here what does it means? My VDS is lesser than the overdrive voltage. So what is the overdrive voltage? That is the difference between gate to source voltage and the threshold voltage. Okay, so this you have to keep in mind that whenever my NMOS transistor is in linear region, then my drain to source voltage is lesser than the difference between gate to source voltage and the threshold voltage. Okay, and in this picture we are not considering any body effect. If there is any body effect, okay, suppose the source is connected at a higher potential than the body, which means my source to body potential is positive, and this is only for an NMOS, keep in mind. Then my threshold voltage is higher. Say my source and body are connected to the same potential, then my VSB will be 0, then my threshold voltage is minimum. But if my VSB is increasing or say is greater than 0, then my threshold value is going to increase. Okay, then my overdrive voltage will also reduce because VGS minus VT, but your VT is increasing, so your overdrive voltage is also reducing. Okay, let's not go into too deep into the body bias because it requires the energy band diagram and other things, so let's not go in deep into it. Okay, so let's focus into this question. So the NMOS is already biased in the linear region, it has been said. So you know the equation that ITHZY is equal to mu n into COX into W by L into say the overdrive voltage into VDS minus half VDS square, which is given in the equation. Now if you just put the value that IDS is equal to 5 micro and your mu n COX into WL, W by L is not changed and mu n COX is also not changed because these are W and L are the device means already it has been fabricated. Okay, now your effective width and effective length you have got it. Okay, there can be mismatch, systematic mismatch, random mismatch, but still your W and L you have got it, and mu and COX, yeah, that also you have got it, and it is for a particular PVT. So just consider that mu and COX is also constant for a particular PVT, and WNL already came from the boundary, so it is also fixed. Okay, so now you don't know what is VGS and what is VT, but if you just take it as a difference, then you can see that your VGS minus VT, which is my overdrive, that was actually 1.05. It means my gate to source voltage was 1.05 voltage above the threshold voltage. Okay, here I don't know what is the threshold voltage. Okay, and even I don't know also that what is my source and body, what are the voltages at source and body. Okay, so I am just considering the threshold voltage, but the fact is that as I mentioned earlier, that if my source and body are connected to each other and for an NMOS, then my threshold is minimum. As my source to body voltages increases, then my threshold also increases, and then my overdrive voltage will also decrease. Okay, so now what they have said that VGS is keeping VGS as constant, and then they are increasing the VDS to 1.5 voltage. Now if my VDS has been increased to 1.5 voltage but VGS is constant, so if VGS is constant, then my VGS minus VT, that is also constant, that is also 1.05. And also I think I should tell you that VDS is increased, mean the drain voltage has been increased, but since the drain voltage has been increased, nothing was applied at the body, so there was no change in the threshold voltage. Okay, so if your drain to source voltage, which is 1.5, if that is greater than your VGS minus VT, then naturally it is in saturation. So now if you just compute the equation for saturation, which is half mu n COX W by L into VGS minus VT whole square into 1 plus lambda VDS, then one thing I want to tell you that this 1 plus lambda VDS is because of the channel length modulation, because as you increase the drain voltage, there will be more reverse biased, and because of more reverse bias, there will be depletion near your say gate to drain area. There is more depletion region, and that is why your effective channel length is reducing. Okay, but we are considering for simplicity, we are considering this lambda, which is the channel length modulation parameter, as 0. So then my saturation current is IDS equal to half mu n COX into W by L into VGS minus VT square. Now if you calculate, you know mu n COX W by L, you know VGS minus VT square, then you will get a particular current. Okay, but in the question it is said that what is the transconductance. So what do you mean by the transconductance? Transconductance means that if you are changing the input, So what output you are getting, it's a ratio between the input current, means it's a ratio of, or you can say it's a derivative of the change in the current, in the output current, which is the drain current, with respect to change in the gate to source voltage. Okay, so what are you going to get? You just take a simple derivative, that you will get mu n Cox into W by L into VGS minus VT. Now if you just replace those values, you will get 52.5 microampere per volt, and this is my answer. Okay, now suppose this earlier I had already discussed with you that there was a 1 plus lambda VDS term. Okay, now let's discuss how this 1 plus lambda VDS term is going to create trouble for you. Okay, so suppose there is a current I naught which is flowing through transistor M1, and there is another transistor which is Mosfet, which is connected M2, but over there the VGS are the same. VGS are same, say by lambda for both of the transistors are same. Threshold voltage, which is VT, that is also same. The product, which is mu n Cox, that is also same for both the transistor. Only factor is that the W by L ratio is different for the two transistors, M1 and M2. For simplicity, I am keeping this W by L1 divided by W by L2, this ratio, say, which is equal to K. Okay, for simplicity, I am considering this value as K. Okay, now because there is a difference between VDS1 and VDS2. But how this is occurring? For transistor M1, you can see the transistor M1 is connected as a direct connected. So your VGS and your VDS both are same over here, because drain and gate are connected to each other. It means that your VDS is anyhow greater than your VGS minus VT. So it is anyhow, it is in saturation. But what about transistor M2? The drain and the gate are not connected. Okay, so whatever gate to source voltage you apply, okay, depending upon the drain to source voltage of M2, your current IR is going to flow. So your current I1 is going to deviate from IR. Now if you just divide this IO equation with IR equation, then you will see that there is a term 1 by lambda 2 VDS2 in the denominator. Okay, now if you do the binomial expansion, then what you will get? You will get two terms in the numerator. What is that? Is 1 by lambda 1 VDS1 whole multiplied by 1 plus lambda 2 into VDS2. Now if you do the multiplication and you just ignore that lambda 1 and lambda 2 term, there is a product you will get like lambda 1, lambda 2, VDS1, VDS2. Just ignore that fact. Then what you will get? You will get like 1 plus lambda into VDS1 minus VDS2. Here I am considering that lambda 1 and lambda 2 are same. Okay, just for simplicity, and I am considering that the channel length modulation for M1 and M2 are same. Okay, so lambdas are same. So still, so if there was no mismatch in VDS1 and VDS2, then you can see your current is, so then the lambda part is 0, only you are left with this one term. Okay, so what you will get? Your current I naught is say K times of IR, or your say IR is what? IO divided by K. But if there is no mismatch. Okay, so now we are going to discuss some of the gate questions where there is this kind of current mirrors are there. So we will just discuss that how this current mirroring option occurring, and we will not consider this VDS1 and VDS2 mismatch. Okay, else it will be, we can land into more trouble. Okay, let's start. Question was asked in gate 2023, where you can see that 1 milliampere current is flowing through this transistor whose W by L ratio is 1. For simplicity, let me just mark this one, this MOSFET as M1, this one as M2, and this one as M3. So you can see that the gate to source voltage, or say the source to gate voltage for these three PMOS, M1, M2 and M3 are same. And we are not assuming, and we are just assuming that the drain to source voltage are same for all the PMOSs. Then what you will see that 1 milliampere current which is flowing through MOSFET M1, that will be mirrored to the M2. But then 10 milliampere current is going to flow through this M2. Okay, and the same one which is over there M3, there 7 times the 1 milliampere current, there 7 milliampere current is going to flow. Okay, so now this from this M1, in the down there is another NMOS. Over there also the same 10 milliampere current is flowing. Here there is no dependency. Here it's a series connection, so the same current has to flow. So this NMOS, from this NMOS where your W by L is 10, there also your 10 milliampere current is going to flow. But if you see in the right PMOS, in the right NMOS, I'm saying, there the W by L is 5. So your VGS is same over there. And I am again saying that I am not considering any mismatch in the drain to source voltage. So what current is going to flow through that NMOS which has a W by L of 5? There the current will be half. instead of 10 milliampere, which was in the left NMOS, there how much current is going to flow? There only 5 milliampere current is going to flow. But at the top PMOS, you are seeing that there is 7 milliampere current is flowing. So across the resistor, there will be 2 milliampere current which is flowing. Okay, so what is your VL? So what is your VL? As 2 milliampere current is constantly flowing through the 1 kilo ohm resistor, so your VL is nothing but 2 volt, because 1 kilo ohm multiplied with 2 milliampere. So your VL is 2 volt. That is my answer. Go to the other question. Okay, so here you can see that 1 milliampere current is flowing through this transistor, which has a W by L ratio of 2, and this is an NMOS. So this current will be mirrored into the NMOS, which has a W by L ratio of 3. So what is the current which will be flowing in through the NMOS, which has a W by L ratio of 3? That will be equal to 3 by 2 ampere. That will be 1.5 milliampere. Okay, so now you can see your V1 is 0, and if there is a current which is flowing in the NMOS, then your value, which is the drain to source voltage, has to be greater than 0. So anyhow, if your V1 is 0, so naturally this transistor, which has a W by L ratio of 5, and where your gate is 0 voltage, your source is greater. So anyhow, this is in cutoff. There is no possibility, because your VGS is lesser than 0. Okay, so the left half of this differential amplifier, you can just remove with this part, because there will be no current which will be flowing through this PMOS, which has a W by L ratio of 10, and this NMOS, which has a W by L ratio of 5, and where your gate is already connected to 0. So this is not possible. So your entire 1.5 milliampere is just going to flow through the right part, which is where you are seeing that there is a PMOS where your W by L ratio is 10, and underneath it there is another NMOS which has a W by L ratio of 5, and your V2 is connected to VDD. Okay, so entire current is flowing, that is 1.5 milliampere that is flowing. And now you can see that at the top there are 2 PMOSs where your gate to source voltages are same. So your current will be just 4 times, because W by L ratio, if you just compare the W by L ratio, then what you will get? 40 divided by 10, so it will be 4 times current. So what will be the current? Your current will be then 6 milliampere current that will be flowing through at the output. Okay, and this output, don't think that this is an open circuit. It is going to some say it is just acting as a current source, and it is just delivering current to some load. Okay, don't consider that this is an open circuit. Okay, hope that the DC biasing conditions and the concept of this current mirroring action is clear to you. Okay, so I am ending my video today over here, and if you have any doubt, then please comment in the comment section. And I have seen that someone has already commented, and after that, when I have replied, it actually helped them in clearing their concepts. Okay, it's always better to have a good concept. Okay, so to have a crystal clear concept, if you have any doubt, then for just clearance, you just comment okay, on the below. And if you just like the video, then like it and share with your friends. Okay, and subscribe to our channel to get updated with our next upcoming videos. Okay, and all the best, guys, and study hard, study more and more questions, because for GATE, if you practice more and more authentic questions, then it is always better for you. You can practice from your standard books like Razavi or Cedar Smith. I'm not publicizing anything, but I'm just saying, for analog I'm saying. So if you just practicing good questions, and then you are solving, say, the GATE questions, okay, then actually you are going to get a lot of positives out of it. At least your concepts will be clear. Okay, thank you, all the best to everyone, goodbye.